Let's do this thing. Welcome. My name is Whitney or Whit. Either one is fine. I have no preference. And I am a GMAT, GRE, and EA instructor here at Manhattan Prep. And I have been all of those things for a really long time at this point. So I'm excited. Today we are going, or tonight, I guess, we're sitting here March 13th, Sunday evening here on the East Coast of the US. We are going to be talking about ratios. And so often ratios are something that we talk about as sometimes like the redheaded stepchild of the fraction, decimals, percents world. Like fractions, decimals, and percents, they get all the glory. And it's really unfortunate because ratios aren't just a concept like, oh, you can write something as a fraction, you can write it as a ratio. But I like to think of ratio as a technique. It's a way to solve certain types of problems. And so that's what we're going to do tonight is we're going to talk about how do I use a technique of ratios to solve a bunch of weird word problems. So I want to get us started with a little bit of a concept of what it means for something to be what I would call multiplicative versus what I would call an additive relationship. So that's the first place we need to start. So if I were to tell you that Marty has twice as much money as Whitney, lucky Marty, has twice as much money as Whitney, or there are 3/4 as many apples as bananas in the basket, right? Or there are 50% fewer people in group A than in group B. These are all what I would call multiplicative relationships, right? So we're multiplying something by a number or a proportion or a percent. So it's crucial that we recognize when something is multiplicative versus when something is additive. So additive would be there are 5 more apples than bananas. There are 3 more than half as many. There are 3 more than half as many girls than boys, or we'll say dogs than cats. I know the GMAT still gets into the whole gender duality, but we're working on not doing that. And slowly the GMAT will join in that whole thing. So there are 3 more than half as many dogs and cats. There are 15 fewer people in group A than in group B. So the first 3 are multiplicative in the sense that I'm giving a proportional relationship between 2 quantities. Whereas the second set of 3 would be more additive or hybrid, where I'm giving you more like an actual concrete numeric difference between items. So note that Marty having twice as much money as Whitney could mean that Marty has $2 and I have $1, or she has $2 million and I have $1 million, which would be cool, but I don't. Versus there are 5 more apples than bananas. The difference between apples and bananas, no matter how many we get, stays 5. So Marty having twice as much money as I do, we like scale up in that way. So again, from $1 to $2, which is only a $1 difference, all the way up to like $1 million to $2 million. Now there's $1 million difference between the 2 of us. Whereas 5 more doesn't have the same multiplicative scaling. So I point this out because what we're looking for when we are trying to deal with ratio problems, right? This technique of ratios, we are looking for problems that are presented in a multiplicative way. So when we have a multiplicative relationship, what I want us to start looking for, and so let me get us our to-do list today. What I'd like to do is start to encourage you to see this idea of multiplicative as ratio problems. And that's not always going to work this way. And there'll be sometimes some other techniques that work as well, or maybe even better in some cases. But for now, tonight, or this morning, we are going to work on how to take these multiplicative relationships and cut out a ton of the math and the algebra by setting them up as ratios. So we have 4 steps. Yeah, 3 more than half as many dogs. Yeah, I don't know. I may have written that crazily. 3 more than half as many dogs. So the number of cats would be 3 more than half the number of dogs. So the number of cats would be the number of dogs cut in half, but then added 3 to it. Yeah, exactly. So that could mean that if there were 100 dogs, there'd be 53 cats. I think it'd be the other way around, actually. Yeah, I wrote it all weird. How about this? We'll just say that my translation's terrible. But the point is I wanted you to see the number part of it, right? The 3 more as opposed to 3 times as many. Yeah, it's Sunday. Okay, so what I'd like for us to do is start with a piece of, oh, I lost it. Here we go. Let me give that back. So I'd like to start with a question and look at how we would go about treating this as a ratios problem. So I want you to go ahead and try this one. There's a problem on the board, whatever. Here's your warm up. I'll set a timer for you. We'll take about 2 minutes to solve. Send me your answer privately in the chat window. And then we'll talk about how this is in fact a ratio, or maybe how it's not, right? We'll talk about how to set it up. All right. If you haven't done so, start to get me an answer. And send it to me just like host and panelist is good, or ooh. Okay. I have 2 answers in. Ooh. This is exciting. This is exciting. All right. So in about 2.5 minutes, let's pause. And yeah, like this question, I love that. It's like, this is the reason why I'm here, because I have no idea what's happening right now. So the first thing I want to note is that this is multiplicative. There are 3/5 as many apples as bananas. There are half as many bananas as cherries. Yeah. So what we'll do when we start to look at multiplicative relationships, step 1, every relationship, and traditionally this will be between 2 things, every relationship between 2 things will get its own ratio. Now, you can certainly write ratios as fractions, but I am going to encourage you for this lesson to write ratios as colon ratios, meaning X colon Y. And so we'll start with our first ratio is 3/5 as many apples as bananas. So let's start with a ratio of apples to bananas. There are 3/5 as many apples as bananas. So there are 3/5 as many apples. There's fewer apples than bananas. And in fact, if I were to have 5 bananas, I'd have 3/5 as many apples. Okay. So for every 5 bananas, I have 3 apples. Okay. So one relationship, apples to bananas. Next relationship is given as bananas to cherries. So it's its own ratio. Now I go bananas to cherries. And it's half as many bananas to cherries. So for every 2 cherries, I have 1 banana. Notice that in this case, the fractions themselves are the ratio, 3 to 5, 1 to 2. Okay. So step 1, everything ends on my paper as its own ratio. Step 2, do we have multiple relationships? Yes. Right. So if we do, then what we'll do is we'll combine these ratios using whatever they have in common. So we're thinking of this like the ratio equivalent of common denominator. So in this case, what that would mean is that I have bananas and bananas. And so that's going to be my common term. I need to bring them together. That means that those numbers have to match. So what I'm allowed to do with a ratio is I can scale a ratio up or down so long as I multiply everything through by the same number. And so maybe let me make a little kind of addendum to this. As long as I multiply every single thing by the same number or divide by the same number, my ratio stays the same. So I'll think, I can multiply or divide everything by the same number. And that keeps my ratio consistent. Think of this like multiplying a fraction, numerator and denominator by the same thing in order to get a common denominator. So I could convert this 1 to 2 into a 5 to something. And so what I'll do in order to do that is I will multiply both items in this ratio by 5. And so again, for a ratio, which one's on the left and the right, it doesn't matter. In the same way that a fraction, we need the bottom to match. This one, it doesn't matter. I just need that same item to match. So my second ratio becomes 5 bananas for every 10 cherries. Now that my bananas match, I can create a single ratio. Apples to bananas to cherries is 3 to 5 to 10. So I've created one single ratio. If I could simplify or reduce this ratio, I might. Essentially, if everything was divisible by the same number, I might reduce it. And then my next step is I need, for whatever it is that I need to solve for, if it's not one of these 3 things, then I'm going to create a new column for it. So the most important sort of column or item in my ratio that I can create is that I am allowed to add or subtract any of these items to each other and create another ratio item. So for example, I could have a ratio item that is just A plus B, or I could have a ratio item that is just B plus C. And in this case, the column B plus C would be 15. I would literally add those 2 numbers together. So this is something we're allowed to do in ratios, is we can add or subtract any 2 items together and put it as a new item. And so the most common way we do that is we create a total where what we're doing is adding all 3 parts, right? So if I tell you, oh, well, what's the total, imagining that these are my real numbers, most people would be like, oh yeah, you can just add them. Fact is, though, is I can add any of them I want or subtract. So if somebody said, what's the difference between A and C? What's the difference between C and B? I could subtract those and make their own column. So for this one, I'll have a total column. I'll add up A plus B plus C. So in my fake basket, I've got 3 apples for every 5 bananas, for every 10 cherries, for every 18 total pieces of fruit. So in my imaginary basket of 18 pieces of fruit, according to the ratios I've been given, 3 of those pieces of fruit would be apples, 10 of them would be cherries, and so on. So I'm allowed to add or subtract. I am also allowed to create any item as a doubled up. So I could have a column for 2A, for example, which in this case would be 6. So I can create a new item in my ratio. And I've built some of these for problems where the ratio is like 4 or 5 pieces long. That's fine. Everything just moves together. I can create new pieces by multiplying a single value times one of my entries. So I can multiply a by 2 or a over 2 and have it by half. I can do any of those things. Or I can add and subtract my items to each other. I'm just not allowed to multiply them times each other. So I can't have item AB, which would be 15. I can't do that. It won't make sense. It would be sort of illogical in the world of my ratios. So fact is, I can add any of them together. And then weirdly and rarely will I sometimes want to double one item. So for now, I'm not going to worry about that. I have a question that says, what fraction of the total are apples, which would be apples over total, which is 3 over 18 or 1 over 6. Now, if there were real numbers given, then I would have to have converted this ratio to match the real numbers, but my problem had no real numbers. So I can treat these amounts as if they were the real numbers. No big deal. So our correct answer is 1/6. How do we feel? Because we're about to do a handful of problems to match it. I know this went sort of slowly. We're going to pick up the pace. How do we feel? So far, so good? Feeling okay? Okay. Killer. All right, let's do it. Let's do it. So for our next problem, let's try this one. So I got a few extra answers in. Nicely done, y'all. Nicely done. So there's a thing I didn't mention. And then if you're new to studying for the GMAT, the thing I didn't mention is that we don't get a calculator. Right? So why does that matter? It matters because some of these multiplicative relationships would actually be pretty easy to just like crank into a calculator. But I don't have one. And so what I'd really like to avoid is a bunch of longhand multiplication and division, because that's slow, it's inefficient, and it's error prone. So what I'm going to do is build these ratios so that I can keep everything in nice, clean integers. And the math often sort of handles itself. So this is something where many of you might have seen a problem like this and thought, smart numbers, which is true. I can pick my own number. There's no real values given, and I can run it through the system, which we're sort of going to do. What I want you to see is that when no real values are given, that ratios can often be the best way to choose the smartest smart number. Like, what real number should I pick? Well, let's let a ratio tell me. So I've got relationships. First, I have a relationship from Monday to Tuesday. Then I have a relationship from Tuesday to Wednesday. Those are two different relationships. So I'm going to write them as two different ratios, which might seem weird, but I'll start with Monday to Tuesday. The price of gold went up by 25%. So that would be like saying it started at $100 and going up to 125. Then from Tuesday to Wednesday, new relationship, we fell by 20%. So that would be like going from $100 down to $80. I don't need these things to match yet. I'm going to get them on my paper. I'm going to clean them up, and then I will line them up. So this one's maybe a little easier to simplify. I'll take zeros out of both by dividing both by 10, and then I'll reduce it further. This would reduce down to 5 to 4. So the ratio of Tuesday to Wednesday is a 5 to 4 ratio. From Monday to Tuesday, both of those numbers are divisible by 25. 25 would go into 100 4 times. It would go into 125 5 times. Now I need to connect these based on the quantity that matches, which in this case is Tuesdays, which in this case already matches. And so my ratio from Monday to Tuesday to Wednesday is 4 to 5 to 4, which means from Monday to Wednesday, the price of gold didn't change. And so my correct answer is C. No real values. I just treated it like the thing it was. I didn't need to create a total for this one. Total didn't actually even really make sense in this situation, but it didn't make sense. So I was never asked to do it. They'll tell me what different items I need, right? They'll fill me in. All right, shall we? Harder? Yes? No? Are we ready for a more challenging one? Because we're going to step this up. Yes, yes, good. Yes. I love it when people want a challenge. Let's do it. Here we go. Stepping up the difficulty. Once again, we're going to shoot for that roughly 2-ish minute mark. All right, y'all. How are we feeling? This was a lot more complicated. Fear not, we're going to keep getting into more and more complicated areas. But for now, this was the most complicated thing we've seen for sure. How was that? Doable? What do you think? Hit me with that. How are we feeling? How are we feeling? I have several relationships. And so I'm going to treat them all separately at first. And I'm not saying this to you because it's like, this is the baby way to do it. When people try to combine relationships too quickly, they make mistakes, period. Like no exceptions to this. So let's get this stuff on our paper. We've got chem to psych. So chemistry to psychology is a ratio of 3 to 4. And that's a P, that's a terrible looking P. And then we have a ratio of chem to bio, that's 4 to 5. Then we have a ratio of bio to statistics, and that's 3 to 2. And my question is, I want the ratio of psychology to statistics. So I need things that match to be next to each other. What I'm going to do is I'm going to rewrite, now that it's on my paper, I'm going to rewrite this as psych to chem is 4 to 3. Chem to bio is 4 to 5. So now I have my chems next to each other. Then I'm going to keep bio to stat 3 to 2. So my bios are next to each other. And then I actually end up getting the ratio I want as psych all the way to the left, stat all the way to the right. I'm making the connection that I want. That part I'm less concerned about. More what I like is to visually get the things that I'm trying to match next to each other. Now I combine these ratios using what they have in common, and I have to do this one combination at a time. So it doesn't matter where you start. I'll just start with these left hand two, but you could have started with the right hand two. It's fine. But I can make a 3 and a 4 both into a 12. So I'll do that. And normally this is kind of how I write it. I do that by multiplying my first ratio through by 4. So 3 times 4, so 4 times 4. And then 4 times 3 to get to 12, so 5 times 3 to get to 15. Now I can turn my 3 into the 15 from this final ratio. So I'm just going to go ahead and do that. I don't need to readjust this one at all. I'll make this 15 multiplied by 5, multiplied by 5. So now I'm going to get this on my paper cleaned up. This is P to C to B to S. And so I've got 16 to 12 to 15 to 10. Now, all I care about is the ratio of psych to stat. So the ratio of psych to stat is 16 to 10. And so I'll reduce those by half and make it 8 to 5. And my correct answer is D. Yay, I'm glad. I'm glad that's the fastest you've done it. So here's the deal. No real values given. I think I can usually sell people on ratios. I'll also say that when no real values are given in a problem, this idea of smart numbers is really powerful, meaning I pick my own numbers. And so when no real values are given, even if things are additive, I can pick my own numbers and throw them at the problem. However, when I start to get a big string of relationships, it can be hard to keep a smart number straight. So anytime I'm in multiplicative, even if I do intend to like pick smart numbers, right? Like choose values and plug them in, I'm still going to set them up like a ratio more than I would ever set them up like an equation. Where we normally start to run into trouble is when we get to questions where there are real values given. Yeah. But before we get to one, I want to try one more question. And it's Roman numeral. But this is going to sort of kick us up to the next level of like, what do I do when they do start giving me real numbers? So give this one a shot. And we'll take again about 2 minutes. I made it challenging again, huh? So why am I making this hard? Well, because I'm mean. No, that's maybe the question is, how am I making this hard? I'm making this hard because I'm alluding to a real number. I'm now starting to say, like, well, there's actually a real number under there. Do you know what it is? And so that can make our sense of multiplicative a little trickier. So if I were to see this problem, I'm like, okay, X, oh my gosh, I got a variable X. You know, I don't want to deal with a variable X yet. Everything is still twice as many as this, half as many as that, blah, blah, blah. This feels like a ratio to me. And so I'm gonna treat it like a ratio, at least at first. And instead of X, I'm just gonna pick an arbitrary amount, like number of beans. So I have some number of beans and twice as many cans of soup. So let me start with beans versus soup. Okay. So I have twice as many cans of soup as cans of beans. So I'm just going to say 1. If I need to bring a variable back in, I always can. But I'll say 1 can of beans, 2 cans of soup. Now, there are half as many cans of tomato paste as there are cans of beans. So new relationship, beans, tomato paste. There are half as many cans of paste as there are beans. So if there were 2 cans of beans, there'd be 1 can of tomato paste. Again, I might rewrite this as S to B and then B to T, just so I can have everything together. So this would be 2 to 1. I just turn it around versus 2 to 1 again. I need my B's to match. So I'm going to double my first ratio, 4 to 2. And then this one's 2 to 1. And so my ratio is soup to beans to tomatoes is in a ratio of 4 to 2 to 1. Now it says, which of the following could be the total number of cans? So first off, I need a total number of cans column. And my total number of cans column would be 4, 5, 6, 7 cans of soup. Now with no other information, all I know is that this is the reduced form of my ratio. I can't reduce any of these numbers any lower and still have a whole number of cans of stuff. So you know what I know? I know that the number of soup cans has to be a multiple of 4, because it could be that I have 8 cans of soup, 4 cans of beans, 2 cans of tomato, and 14 cans total. All right, so this is going to keep, I could multiply it up again. It could be 12, multiply everything through by 3. So 12, 6, 3, and 21. So what are you starting to notice that is going to have to be true about my total number of cans of soup? What has to be true? It has to be a multiple of 7. Exactly right. It has to be a multiple of 7. And that's the only restriction. I can keep moving this up and up and up simply by multiplying it by anything. But that total will still stay multiples of 7. 7, 14, 21, 28. So 28 would work. 46 is not a multiple of 7, which means I'd have partial cans running around. So not 2. So I know that 1 is, that gets rid of answer choice B and E, because I know that 1 does work. And the next multiple of 7 is 63, which means my correct answer is D. So all I know is that the total has to be some sort of multiple of 7. Turns out I didn't even need stupid X. Didn't even need it. But this is going to hopefully get you thinking about what we do when they, in fact, do tell us. They don't ask what's a possible number, but they say, oh, no, there are this many cans of soup, or there are this many, what have you. So we'll go back to our friends, the apples, the bananas, and the cherries. I want to give you a chance to practice setting up those ratios again, and then notice that the question has changed. It is no longer the fraction of total pieces of fruit that are apples. I've now introduced a real number. And the introduction of this real number means that I am completely now outside of my ability to use smart numbers. I don't get, on a traditional version of the way we think of smart numbers, I wouldn't get to pick my own number anymore. I might have to work backwards from the answers or something along those lines. That said, if I stick with ratios, I can solve it just like I do all the other ones when I was allowed to pick all my own numbers. So get this one set up and see if you can figure out what to do with that 54. Nice. So I'm getting a bunch of answers in. What did y'all do? I gave you a real number all of a sudden. What changed? What were you able to do with the ratio in order to incorporate that real number? What did y'all do? Mm-hmm. Nice. No, that wasn't publicly, but okay, you could. So I got a couple different ideas. So one was I could take the answer choices and plug them into the ratio. Right? Totally. We can absolutely do that. This idea of working backwards off of our answer choices. So let's start with our relationship. Apples to bananas is 3 to 5, and bananas to cherries is 1 to 2. And so we break this one up to 5 to 10. Notice that we scaled. So I want to highlight this. We scaled this number by multiplying the same number times everything. So just keep that in mind. So then I got my new ratio of apples to bananas to cherries as 3 to 5 to 10. And it says, total pieces of fruit, basically. So I need a total. In this case, it would be 10 and 5 and 3, and that's 18 again. There is nothing that says I can't just keep scaling this ratio up. So down here, are there real values? Yes, there are real values. And so what do I need to do? I need to convert my ratio to match the real numbers. And so the real number of interest here that we're trying to get to is 54 total. And so I need to figure out, what do I multiply this number by? So if I multiplied it, if I double 18, that's not big enough. But if I triple it, right, like 3 times 20 would be 60. So this has to be 3. This has to be multiplied by 3. So I'm going to multiply everything else by 3, but really all I care about is apples. So I can stop there. And so 3 by 3 is 9. That's the number I'm looking for. C. Okay. I don't care where the real number is that they give me. It could be the total. Could be one of the individual inputs. It doesn't matter. I'm going to build my ratio, and then I will scale my ratio to match the real number they gave me. And now what I want us to do with the next several problems is I want you to see how we can apply this in crazy problems where we wouldn't necessarily consider, right? Like we might sit down and try and do all the math, which, you know, for some of these you can if you want to try. But I want us to think about how do I, right? Like how can I use just these ratios to build this? So give this one a shot. Y'all, so fast. So fast. It's awesome. So fast. Okay, so what can I do? I've got my 3 amounts of time, 2 hours to 3 hours to 5 hours. So this would be like the smallest amount, right? These are my 3 people, A, B, and C, which means the total number of hours worked would be 5, 6, and 8, 10. But I'm told that it actually was 110 hours. So my multiplier is 11. I'd multiply all of these by 11, 22, 33, 55. The difference between the longest and the shortest. So 55 minus 22 is 33. And that's my answer, C. Okay. Let's do it again. Let's do it again. What about, get rid of that. What about this one? How we feeling? Not, oh, some answers are starting to come in. How did this one feel to set up? I'm still only looking at a couple of answers. So how was this one to set up? Easier? I'm going to guess no. What was it about this one that made it trickier? What felt trickier? Feel free to send it to me privately if you don't want to share it publicly, but what made this one feel trickier for you? Yeah, we had percents and fractions, increases and decreases. All right, ready, y'all? So thinking all the way back to the money that was allowed to go up, right, by 25%, back down by 20%. We're gonna do the same thing here. Remember, each ratio or each relationship between two things gets its own ratio. So January to July is one ratio. Fully separate relationship is July to December. So I can pick whatever numbers I want. I'm going to start with January to July, and a stock increased by 25%. So I'm going to go 100 is nice to 125. I'm then going to go from July to December, separate relationship. So July to December, and I need a price that can go down by 1/3. What can I reduce by 1/3? Well, I'll take 3. If I reduce 3 by 1/3, that takes me down to 2. Nobody said I had to be complicated, right? I can do this as simply as I want. So I do the first one in percents, I do the second one in proportions. I'm going to reduce both of these. They're both divisible by 25. So once again, this is 4 and this is 5. Now I have to bring my Julys together on the 3 and the 5. That would give me a 15. I multiply both of these up by 5. I'm going to multiply both of these up by 3. So my ratio is January to July to December is 12 to 15 to 10. Now, what did the problem tell me about December? The problem said that December was 100. Well, that just means that these are 120 and 150. So how much was the stock worth in January? I don't have to pick ugly numbers. This is why, I'll be honest, this is why we keep the relationship separate. Because I want to pick whatever numbers make that relationship the easiest. They do not have to line up at first. We just need to get them onto our paper. And then once we clean them up, then we bring them together. Yeah, so we do not need things to be complicated at first. Our job, and again, this like decrease by 1/3, right? Like that's not an easy concept. I certainly don't want to decrease a number like 125 by 1/3. Like, oh my God, what crazy math. And then I'm having to back up and figure out, no, I'm going to keep my relationships separate. Right? And then bring them together once I've cleaned them up. Yeah. Again, what do you think? Maybe. Let's try it. Let's do it. We're going to do it again. Let's see how you do with this one. Nice, y'all, making this happen. So good, so good. So a lot of times when a person sees a problem like this one, they go right for that number because numbers feel concrete. They're like, oh, let me get that 8,400. And then let me figure out how to take like 4 sevens or 3 sevens, or we don't even know. We just get really confused. We're better off saying, all right, let me get my candidates now. Candidate A to B, that ratio is casting votes in a ratio of 4 to 3. So for every 7 votes, candidate A gets 4, candidate B gets 3. Now, I could use some estimation here. I know that A gets more than B. And so half of 8,400 is 4,200. And so I know the answer is greater than 4,200. And so working backwards in this way or estimating this way is good. And we've got other lessons for that. But for this one straight, like for now, how do I convert 7 up to 8,400? Well, I'm going to start by converting 7 up to 84. I do need to know my multiples of 12. So if I multiply all of these things by 12, I get up to 84. I want A, so 4 by 12 is 48. Then to get those last 2 zeros, I'll toss those on. That'll get me to answer choice D. So I can use the ratio. Often we think, oh, ratios are good when we're bringing numbers together, and they are certainly good for that, right? They're going to save us a ton of headache when we're bringing lots of numbers together. But they can save us a headache even when the relationship is short and simple. So I want to give you one, and this next problem that we're going to do, and yell at me if you've got any questions in the chat window. This next question that we're going to do gives people a ton of trouble because they take the real number and they do some stuff to it that you're not allowed to do. Okay, so give this one a go. Feel free to try it with algebra to see what happens. Like, see what your gut instinct is when you try it with algebra. But then see, like, how would I set this up using a ratio? How can I come up with this relationship? So what I often see happen with this problem, and it may not seem like it, but this is actually a pretty difficult problem. It's rated as very difficult. The official version that this is based on. What happens is that people see this 460 and they think, okay, there are more sales in April than in May, 15% more in April than in May. And so if I take April and just subtract that 15% back off, that should give me May. The problem is if we do that, if we take 15% of 460, so 10%, move your decimal point 1, that's 46. 5% is half of 46, so 23. So that would be 46 plus 23 is 69. If I subtract 69 from 460, I get 391. And everybody who gave me an answer was not A, because you are right. The right answer is not A. So what happens is that people try to do percentages in the same way forward and backward. Because again, we get fixated on this real number. When instead, think about the relationship and get the number back attached to it as you know it. So April versus May, again, the order doesn't matter. April has 15% more than May. So if May had 100, April had 115. What I actually know, though, is that A really had 460. And there's no decimals over here, y'all. So it's going to have to be a pretty clean number that multiplies, because this number is very clean. And so if I look, it's like twice as big. No, 3 times 4. What would 4? Yep, 4 would work. So I multiply both sides by 4. There's my 400B. Keep your focus on the multiplicative relationship. Okay, I'd like to give you an extra wrinkle and show you kind of a unique way that this works out. And so I want to go back to this for a moment. So I'll give us the ratio. We're back to apples, bananas, and cherries in our ratio of 3 to 5 to 10 for a total number of 18 pieces of fruit. Now the question has changed. I want you to think about, how would I get to if there are 21 more cherries than apples? How could I get to that value? 21 more cherries than apples. How do we find it? Hit me with your answer if you think you've got it, but how do we find it? And feel free to type that in the chat window. $21 more cherries. That's an additive relationship, right? I told y'all we're not doing additive relationships. So a couple of you have given me an answer. So if you've given me an answer, I want you to type to me in the chat window how you got there. How did you find that answer? What steps did you take to get there? Ooh. Okay, so I've got 2 people telling me that you just kept multiplying it up. So we didn't need total in this one. So we could kind of ignore our total. But you just kept multiplying it up. So like 6 to 10 to 20 and check to see if that worked. And so on. Okay, and so did a little algebra, found a multiplier. Check it out. This comment down here, you are allowed to add or subtract any of the values. If what I'm looking for is the difference between cherries and apples, well, in this ratio, that's 7. That's 10 minus 3. Yep, exactly. So we find that difference in this base ratio, and I appreciate that you call it out. It's basically what it says. I find that difference. The difference is 7. I know that the difference I want is actually 21. That gives me my scaling factor. So how many bananas? I'd multiply that by 3. I got 15 bananas. So any of the stuff that we need to add or subtract, we can also create an item for. And so now this is a problem I'm about to give you that shows up in our advanced classes. So give this one a shot. Would you believe me if I told you this is just like all the other ones? Maybe. What was it about this one that made it trickier? Because at this point, I've gotten one answer. So what is it about this one that's making it trickier? Oh, I'm sorry. Thank you. See, somebody needs to yell at me. There's a typo in this one. Hold on. So is there? No, wait. 50, there are. Oh, yeah, there's a typo. You're right. Thank you. See, there we go. Let me fix it. Hold on. Let me fix it. It's harder when there's a typo. So if 65% of the students are undergraduate and there are 5,100 more, let's go undergraduate than graduates. Let me fix this. Thank you. So let's say 65% are undergrad, and there are 5,100 more undergrad students than graduate students. Thank you. There's a typo. See, all you have to ever do is if you find something crazy like that, be like, oh, hey, Whitney, there's a typo. All right, so now hit me with that. If 65% of the students enrolled are undergrad, let me make sure the rest of my numbers aren't crazy. You're like, oh, okay, now this is all clear. Let me know when you got it. There we go. Much easier when I give you an actual problem. Makes so much more sense. Makes so much more sense. Thank you for catching the typo, y'all. So I've got undergraduate and graduate students. Undergraduate are 65 out of every 100, which would mean graduate students would be the other 35%. And the difference between undergrad and grad is 30. And I want to know how many students total are enrolled. So to be honest, I only care about these two columns now. So this number is not supposed to be 30. It's supposed to be 5,100. So 3 goes into 51 17 times. And if you're not sure, a shortcut here is 51 over 3 is the same as 30 plus 21 over 3. And I can distribute. 3 goes into 30 10 times. It goes into 21 7 times. So if I multiply this by 17, I get to 510. And so this gets to 1,700. But I need to get to 5,000. So I add one more 0. And that gets me to my correct answer, B. Thank you for fixing it. No wonder. See, all you have to do is say that's what makes it hard, Whitney, is that you wrote it wrong. Nice. Okay, so I can add or subtract. I want you to see how I can take bizarre questions. And so here come the last couple your way. How I can take bizarre questions and still use ratios. Try this one. It's okay if you're still working. This is really tricky. What I want to highlight for this, though, is that reminder that we are allowed to add or subtract any of the values to each other, and we can multiply any of the values by a set number. So I'd be allowed to have things like width to height, but then I could also have a 2 times W, or a 2 times height, or a 2 times width plus 2 times height. I'm allowed to have all of those in the same ratio. Side note. So if my perimeter, that's additive, I can still build off this aspect ratio. So if my width is 16 and my height is 9, twice my width would be 32, twice my height would be 18. And so twice my width plus twice my height, which is perimeter, would be 32 plus 18 is 50. But the actual perimeter is 100. So I double everything. So what is the width? It's 32. So I can even take weird geometry problems, right? Like super weird geometry problems. And as long as things are given in like ratios, and once I get in a ratio, I realize that all I'm doing is adding or combining the values, I can stay in the world of ratios. I love ratios. They're like my favorite thing in the whole world. Favorite thing in the whole world. Other than a typo, how are we feeling? Okay. Last one. Last one. How do I create ratio values for things that are like almost feel like they're missing? I can make a ratio value for anything I want. Right. So I have a value that is 20% greater than Ken, but also 20% less than Lorena. But Whitney told me I'm not allowed to put 3 things together in the same relationship at one time. So I have to kind of think of this for a second. Let me just think of this like missing, unknown, Ken's wish list, right? So Ken and his wish list item, if he had $100, his wish list salary would be $120. Now, the relationship between Lorena and this magic salary is if she made $100, this magic salary would be 80. You clean these up, 8 to 10 or 4 to 5. Let me clean this up, 10 to 12 or 5 to 6. I'm gonna find these two here in the middle. Let's combine those on a 24, 12 maybe, let's go 12. So if I get to 12, I'll multiply this one by 3, so this is 15. I multiply 6 by 2, so this is 10. So Ken, mystery amount, Lorena. Now Lorena actually makes 60,000, which is 4 times bigger. So Ken must actually make 40,000. So I can add items for like whatever I want. I can stick them in there for literally whatever I want. You could certainly work backwards in a lot of these cases. You could certainly use estimation in a lot of these cases. So what I don't want you to think is that this is the only way to solve these. And in fact, usually this is the way we don't always teach people how to solve them. But when I can find the opportunity to set things up in this multiplicative way, it can often save me a lot of time and keep me in real numbers. Yeah. So when in doubt, right, I want you to keep track of this little like multiplicative relationship. So make a little note to yourself, right? If I start to see multiplicative relationships, I'm going to question, like, could I set this up as ratios? So how would I do that? Well, each ratio or each relationship is going to get its own ratio. I'll reduce them and then bring them together if there are multiple relationships, thinking like fraction, common denominator type thing. So scale them up or down by the same amount. Then once I've got them in a combined ratio, I will add new ratio columns, if you will, for any amounts I need. Maybe it's the sum of some of them. Maybe it's the difference. Maybe it's 2 times one of them minus one of the other ones. Like I can have all kinds of relationships once they've been brought together. And then if they didn't give me any real numbers, great. I'm just going to attack it as if the numbers I put on the screen are real numbers. If they do give me real numbers, then I have to scale my ratio up to match those real numbers. And that's it. Now, learning to recognize them, learning to attack them, right? I'm not saying this is simple. It's definitely not. But what I want you to see is that this is a method that can be useful in a lot of different types of questions, right? At different content areas. Yep. But it does take practice and looking for it. So what I would recommend is, we'll have this posted on YouTube if you're watching it on YouTube, right? Like obviously you can just bookmark this page. But I would say that this would be something where come back to the lesson in a week or 2 weeks, and you'll see the timestamps let you click straight to the questions and come back through and try out some more of the questions in a week or 2 weeks from now, so that you can see like, okay, now I'm 7 days later, do I still recognize that these are multiplicative? Do I still see how to set up the ratio? Yeah. All right, y'all, you did an amazing job this evening. Just to highlight for you, if you have not already, you are always welcome to sit in on any of our classes. Our session ones for any online classes are always free. You can go to our website, manhattanprep.com/GMAT/classes and free, whatever. Just go to our website. You'll see a huge menu of all the stuff that we have for free. You can also take a free practice test. Right. So make sure you can grab a free GMAT, also take a free GRE if that's what you're looking for. Yeah. And by all means, right, reach out. We've got an entire free prep hour YouTube channel, and we've got 80 some odd video lessons there that are all an hour or longer. These are some of my favorite things to teach. So you'll see us there. And we've got the GRE ones, and there's usually some decent overlap. So feel free to check out some of the content that we've done on our GRE site. Our free prep hour as well, right? These 2 tests cover a lot of the same material. I do have a couple of extra questions in the Q&A panel, but otherwise, if you don't have any questions, thank you so much. Feel free though to post them in the chat window if you do have questions. CR, I was surprised to find out that every assumption was a strengthener, but not vice versa. Why is that? And so the thing is just because something makes an argument stronger. So I want to put this on the board so that people can see it, because that way it'll make it easier for you to understand what it is that I'm saying. So the question was, all strengtheners The Jerry and the GMAT prep hours are not the same. We have different prep hours, but the content that the two tests cover is the same. And so often if you're looking for something, but you can't find it on our GMAT free prep hour, say geometry is way more common on the GRE. So go to our Manhattan Prep GRE page, check out the free prep hours there, and you'll see that we have a ton of geometry ones there as well. Yeah. And then we've got, I do. Some of you have hung out with me before. You know that I have a free prep hour, big giant toolkit. And so let me give you a copy of it. This will give you a chance to copy it. It's got all of our free prep hours, quant and verbal. If you're watching online, feel free to reach out. It's wgarner@manhattanprep.com. And I'll send you that link to this free organized prep hour Excel sheet that I've created. And that way you can see all of the different topics there. But you can find oftentimes more geometry on the GRE side. The GRE and the GMAT both also have reading comprehension. So if you're in need of some additional verbal support, sometimes the GRE practice sessions, those free prep hours, can be a useful tool for that as well. So there, that link should help you. Hopefully that comes through. Let me know if that's not loading for anybody and I'll see if I can fix it. But so Jaideep, to your question. So the question here is, and I'm just going to copy it out, right? For CR, every assumption is a strengthener. But just because something strengthens doesn't mean it is an assumption. So the biggest thing to think about when it comes to assumptions is that an assumption is something, at least for the GMAT and the GRE, an assumption is something that is required or necessary for the argument in order for it to survive. Yeah. So a requirement, right? An assumption is required. So I can offer up a strengthener. It's good for my argument, but I didn't need it in order to survive. So let me give you a very dumb, but hopefully illustrative example. So apologies for the sort of dumbness that this is about to be. So imagine I give you the argument. Maddie, sorry, let me do this way. All dogs love peanut butter. And some of you who've hung out with me before will have heard this. Love peanut butter. Therefore, Maddie loves peanut butter. I'll start with this one. And then let me give you some options. One, Maddie loves all kinds of treats. Maddie is not a cat. Maddie loves to play fetch. And then I'll give you one that's a little more realistic than this. So in order for me to draw this conclusion, right? So here's what I know. I know that all dogs love peanut butter. My conclusion here is that therefore Maddie loves peanut butter. Clearly, she loves it. It's the best. So what am I assuming? So the easy assumption that most people think of is like, we're assuming that Maddie is a dog, right? Like that's a requirement. If Maddie's not a dog, this argument falls apart. That said, things that might suggest that she's a dog, while that might help, they aren't required. So the fact that Maddie loves all kinds of treats, and even if I were to say Maddie loves all kinds of dog treats, that might make me think, yeah, okay, maybe Maddie does love peanut butter. If dogs love peanut butter and Maddie loves dog treats, then maybe Maddie loves peanut butter too. But that's not a requirement. Maddie could not love all kinds of dog treats. She could really be very picky. I have a dog. Her name's Maddie. She is very picky. But she does, in fact, love peanut butter. because she's a dog. So this, Maddie loves all kinds of dog treats, might make me feel better about the argument. Right? This might strengthen the argument, but it's not a requirement. The only requirement in order for this argument to be true is that Maddie is in fact a dog. That's a requirement. That's the assumption. A strengthen is just something that it could be as strong as an assumption if I wanted it to be, or it could just be something that makes me think the argument is possible. Like, I don't know, that sounds maybe more reasonable. Number 3, for example, the fact that Maddie loves to play fetch might strengthen my belief that she is a dog, but it's not a requirement for the argument. Maddie does not have to love to play fetch to love peanut butter. She just has to be a dog to love peanut butter. So in both of these cases, I have strengthened. They make me feel better about Maddie wanting peanut butter because they make me think that, yeah, okay, maybe Maddie is a dog or she's dog-like. But they aren't assumptions. They're not necessary for my argument. The second one, however, is necessary. It is a requirement. And so what I find is, kind of to add to this piece up here, is that strengtheners feel like strengtheners. Not all assumptions feel like they're strengthening, because what they're doing is making my argument possible at all. And so often when we look for assumptions, and I did a whole lesson on sort of critical reasoning assumptions, I think pretty recently, actually. There is like a whole assumption family one. I'll have to dig up, but it's in some of the more recent free prep hours. If you want to get more into this like assumption family and how you cover it. But often what I'll ask if I'm trying to decide if something's an assumption is I'll ask the question, did I need it to be true? Is this required? That's really what makes an assumption an assumption. Is it required? So if I were to say, let's pretend that this was wrong. Let's say Maddie is a cat. Well, if Maddie is a cat, then my argument dies. Because the only thing I know is that dogs love peanut butter, not that Maddie loves peanut. Like, I don't, right? Like, in order for Maddie to love peanut butter, she has to be a dog. In order to be a dog, she can't be a cat. So anything that says like Maddie's not a cat, she's not a rock, she's not a horse, she's not a human, she's not a whatever, all of those things are a requirement. All right, let me give you a more realistic one. Okay, so let's add to this one, a slightly more realistic version. And this is one where I often try and get my students to come up with assumptions. So the argument is Z-Phone. So Z-Phone's revenues recently increased dramatically. Therefore, Z-Phone's profits must have also increased dramatically. So for this one, I want you to type it to me in the chat window. Right. So I definitely give me this in the chat window. What is the author assuming? If Z-Phone's revenues recently increased and therefore their profits must have also increased dramatically. And thank you, Alyssa. That's really kind, by the way. That's very kind. What do you think, JD? What is something I would assume? And anybody can jump in. What have I assumed? Yeah, okay, so I'm getting some that are coming in. These are great. These are great. So I've got costs have not increased. Costs have neither, or must have either. Costs must have stayed the same or decreased. Their marketing skills are terrible. Right? What else? I get some other ones. I get costs went down. Costs stayed the same. So y'all, it turns out that all of these are strengtheners. all of them strengthen my belief that if my revenues went through the roof, my Z-phone, my profits must also have increased dramatically. All of these are strengtheners. That said, none of them are assumptions. None of them are assumptions. Yeah, and I love that. Like, so I got another one. It was like Z-phone sold more phones. I have no idea that they sold more phones. I don't know why their revenue went up. They now charge $4 billion per phone and they sold one, right? Like, I don't know, right? So all of these strengthen because they're all getting at this hole in the argument between profit and, like revenue and profit, which is cost. Y'all all were thinking like cost. The fact is though, is that while every one of these would certainly help my conclusion, none of them are required. And so the assumption is often written in very weird language. It will often eliminate the one worst case scenario. So the only thing that is actually a requirement, the only thing that's actually an assumption in this case, is that Z-phone's costs didn't increase so much as to offset the large increase in revenue. So it could still go up. Costs could still go up somewhat. They just can't go up so much that they offset the entirety of this dramatic increase. So notice that all of the things that are on the board would strengthen, like costs not increasing. If I knew that costs hadn't increased, that would certainly strengthen my argument. But it's not a requirement. Costs are allowed to go up. Just not a ton, but they are allowed to go up. And costs didn't have to stay the same or go down. They could have, again, gone up by a little bit, right? And so often what we want to think about is strengthen means, rather than this, like every assumption is a strengthener, but just because something strengthens is not an assumption. I'll be honest, like that feels good on paper because it feels really like theoretical. But here's the argument I would make. This is how I would think about these two types of things. And again, I have a somewhat feeble brain when I'm like packed into a whole lot of time. And so on a test, I'm like, I got to keep stuff simple, or my poor brain is like shorts out, right? And so what do I look for? I say that an assumption is required. I have to have the assumption. Without it, my argument dies. So a way to think about assumptions are assumptions make my argument possible. When I think about a strengthen is anything that's nice to have, but not necessary. I don't have to have costs go down. That'd be cool if they did, but I don't have to have that be the case. If I were coming up with an intervention to get people to stop smoking, and the intervention was to charge $4 million per every pack of cigarettes, would it help my mission if people realized the safety issues with smoking cigarettes and wanted to quit? Sure, that would help my conclusion that, I want people to quit smoking. That would help. But my actual argument is that I'm going to charge you a whole bunch of money to get you to quit smoking. So the assumption isn't that you want to quit smoking. The assumption is that you don't want to spend $4 million per pack of cigarettes. So strengthens are anything that are nice to have. It's like, well, that'd be cool. That would help my conclusion. But does it have to be true exactly that way? And so the reason why we often bring this concept of assumption and strengthen, we talk about them together, is it's easy to mix them up. That an assumption is a more elemental strengthen. That often we move from something being an assumption to a strengthen because we add too many details. So for example, what I want for my assumption is purely that our our costs didn't go up so much that they ate up our entire increase in revenue. That one weird situation, I had to wish it away. Otherwise, I don't have to be really specific about what does happen. I'm more often going to be specific about what does not happen. So hopefully that cleared up a little bit of this like assumption strength in business. I think that logical, every assumption does in fact strengthen an argument, but not all strengtheners. The reason for that is that not everything that strengthens is as important as an assumption. An assumption is bedrock and this like necessity. A strengthen is just like, well, that would be cool. That would make the argument seem better. It doesn't have to be true, but it would certainly make it sound better. So strengthens are often much softer. Assumptions don't always feel great, but they are in fact giving us like a foundation to stand on. Yeah. All right, hopefully that helped. All right, and if you have any other questions, feel free to keep joining any of our free prep hours. We're happy to help. Again, my name is Whitney or Whit. By all means, reach out to us. Come check out a free class. Come join us for more free prep hours. Come hang out with us for more, free quant workshops and so on. And otherwise, have a lovely rest of your evening. And hey, happy Pi Day Eve. It's almost Pi Day. 3.14, y'all. It's tomorrow. Go out, eat pie, do math. All right. Bye, y'all. Have a good night.